7.2, graph exponential decay functions. This is very similar to what we saw in 7.1. 7.1, we saw graphs that got steep on the right. That was called exponential growth. And that could have happened either with a positive or negative growth. Exponential decay is kind of a reflection across the y-axis. Instead of getting steep on the right and flat on the left, we're going to get steep on the left and flat on the right. And once again, that could be either right side up or upside down. So decay and growth look the same, it just changes the side where the steepness occurs. Back in 7.1, that base was always greater than 1. If you go back and look at your 7.1 examples, you'll see that all of the bases were bigger than 1. In exponential decay, the base is always less than 1. For instance, we might have 1/2 to the x, 2/3 to the x, and so on. That base will be less than 1. So right here in the key concept box, we kind of have a picture of all of the key features of an exponential decay graph. The important part is on the parents, there's still an asymptote at y equals 0. That will shift just like it did in 7.1 for the growth graphs. All of the decay graphs will get steep on the left, flat on the right, always. Domain is still all real numbers. Range is still always determined by where that asymptote is. If it's above the asymptote, we'll say y is bigger than wherever that asymptote is. If the graph is below the asymptote, then we'll say y is less than whatever that asymptote is in this particular graph, like so. Exactly the same as exponential growth. Side quest time. We're going to look at what a table for one of these guys. So we're going to call this example 1a. If we try making a table like we did for growth, remember we put in 0, 1, and 2, we're going to get 1/2 to the 0, 1/2 to the first, and 1/2 to the second. The 0 is okay. Anything to the 0 is 1. Then we start getting fractions. 1 to the first is 1, 2 to the first is 2. 1 squared is 1, 2 squared is 4. Personally, I don't like fractions. So when we do these exponential decay problems, we're going to rewrite this a little bit. You might remember from Algebra 1 that if you're trying to evaluate something like 2 to the negative 4, the way we rewrite that would be 1 over 2 to the 4th. Alternatively, if we saw something like 1/2 to the negative 4th, we could rewrite that as flipping the fraction 2 to the positive 4. This is a useful idea. Moral of the story, if we see a to the x, we can rewrite it as 1 over a to the negative x. Let me talk about why I'm telling you this. Our actual problem has 1/2 to the x. Because this base is less than 1, I'm going to rewrite this using a negative exponent. I'm going to rewrite it as 2 to the negative x. Where I get the 2, I flip the fraction. 1/2 gets flipped to become negative, or to become 2. And that means I change the sign of the exponent. Now I'm going to make a new table. Instead of putting in 0, 1, and 2, let's see what happens when I do this. 2 to the negative 0 equals 2 to the 0, which is 1. 2 to the negative of negative 1 really means 2 to the first, 2. Negative 2. Oops. Two to the negative 2 equals 2 to the positive 2, 4. Notice I'm not dealing with fractions anymore. Moral of the story, anytime you see a number less than 1, like it could be 1/4, to the x, the way we're going to rewrite that problem is flip the fraction, change the sign of the exponent. Those two statements are equivalent, meaning they're exactly the same. So let's see how that looks in our example 1. I see a base that's less than 1, so I'm going to flip it and make the exponent negative. Because the exponent's negative, I'm going to still put in my 0, and I'll put in my negative values for x. I'm choosing negative values for x because a negative times a negative makes a positive. From the previous slide, we see this is going to be 1, 2, and 4. Asymptote, because there was no shift, this is our parent function. Parent functions always have that y equals 0 asymptote on exponential functions. There's no shift this time, so I get to go straight to the graph. Looks like my y values need to go up to 4. My x values need to go out about 2. And I plot my points. 0, 1, negative 1, 2, negative 2, 4. And you'll notice that it got steep on the left instead of the right this time. And that's really the only difference between 7.1 and 7.2. Domain, just like exponential growth, we're allowed to have any x value. So we say all real numbers. For range, also similar to last section, we only want the numbers above the y-axis, or the x-axis. So we say y is greater than 0. Done. Side quest time. In your notes, I'm going to put up 3 problems that I want you to evaluate on your own, and then we'll go on to the actual example. Go ahead and pause the video and try to evaluate these on your own. See if you get the same thing I do. Hopefully you remembered anything to the 0 power is 1. 1 times 3 is 3. These next two have the negative exponent, so your first step should have been to rewrite this by flipping the fraction and then changing the sign of the exponent. 2 over 5 is the first, just 2 over 5. Now we get to multiply, we get 6 over 5. Once again, we have a negative exponent, so we flip the fraction. 3 is really 3 over 1 times 2 squared is 4, 5 squared is 25. And we get 12 over 25. These fraction skills are going to be relevant in the next example. So once again, we look at a couple problems without a shift. Remember, if we had a shift, we'd see something like a -2 plus 4 or something similar. We'll see that in the next example. So we just start off by first rewriting our function, because we don't like that fraction less than 1 inside the parentheses. And now I can make a table. And because of the negative exponent, I don't want to say 0, 1, 2. I want to say 0, negative 1, negative 2. Anything to the 0 is 1 times 2, 2. 4 to the negative of negative 1, 4. 4 to the negative of negative 2, 16. Don't forget to identify your asymptote. No shift. So we can start drawing this. Looks like I need to go all the way up to 16. And on the x-axis, I should go out a couple units. So we plot our points. 0, 2, negative 1, 4, negative 2, 16. Once again, we see that this is decay. Put the dotted line in for your asymptote. Should have done that first. And we can identify our domain and range. If you draw your graph and it doesn't look like decay, when you know it's a decay graph, you should go back and figure out what you did wrong. You'll know it's a decay graph if the original base is less than 1. Domain, all real numbers. Again, that comes from the fact that anything on the x-axis can be used. Range, y is greater than 0. I think part B gets a little harder because of that messier looking fraction. You should recognize that 2/5 is less than 1, so you should be rewriting this. You don't like fractions less than 1 for these, it makes it a little harder. Beyond this, we make our table just like we're used to. Put in our 0, negative 1, negative 2. Anything to the 0 is 1 times negative 3. 5 halves to the negative 1. 5 halves to the negative of negative 1, I should say, makes it positive 5 halves. So negative 3 times 5 halves, which is negative 15 over 2. We want that as a decimal so we can graph it. Next up, we have negative 3 times 5 halves to the positive 2, which is really 25 over 4. And we get negative 75 over 4. Once again, we'd rather have this as a decimal so we can graph it. And we need to identify our asymptote. Because there's no shift, that stays the same. And we plot our points. Looks like we need to go all the way down to negative 25 about on our y-axis. X-axis, as normal, goes out a couple in each direction. So I start plotting my points. First one up, 0, negative 3. Then negative 1, negative 7.5. And negative 2, negative 24.5. Notice this is still exponential decay because it gets steep on the left, flat on the right. It flipped upside down right now. You should be able to look at the original problem and tell me why this whole thing flipped upside down. If you decided it flipped upside down because of the negative, you're right. All that's left is to identify the domain and range. Once again, and I promise this is going to change here probably in the next couple of sections, because we'll be out of this type of graph. For now, the domain is still all real numbers. Range, we're not above the x-axis anymore, we're below. So we don't want y bigger than 0, we want y less than 0. Next up, pause the video, practice all 3 of these. I'm looking for the graph, I'm looking for a table, I'm looking for your domain and your range. Last example that we'll be looking at is exponential decay once again, this time with a shift. Just like in 7.1, the first thing you need to do is identify the parent function, which means rewrite the function without the shift. Then my recommendation is we look at that base, we notice it's less than 1, so I rewrite that using a negative exponent. Now I can make my table. 0, -1, and -2. Choosing negative because of the negative exponent. Fill that table in. Anything to the 0 is 1 times 3, 3. 2 to the negative of -1, really 2 to the first. 2 times 3 is 6. 2 to the negative -2, it's really 2 to the positive 2. So 4 times 3, 12. We don't graph yet. This time, we have to apply the shift. We should be familiar with shift by now. That x plus 1 in the original problem tells us to go -1, -2. I change the sign on the x shift. I leave it alone on the y. Nothing new there. Next up, we apply that shift. We subtract 1 from every x value, and we subtract 2 from every y value. Pause the video and try to fill that in yourself before I do it for you. So subtracting 1 from every x value makes it -1. -1 minus 1 is -2. -2 minus 1, -3. Subtracting 2 from my y values. 3 minus 1, or 3 minus 2 is 1. 6 minus 2 is 4. 12 minus 2, 10. At this point, we're ready to draw the graph. No, we're not. I left something out. Pause the video and try to figure out what I left out, and then I'll talk about it. I did not include my asymptote here, the one time that it was most important. It's important now because the asymptote also shifts, just like last time, by the same value as y, the y shift. So first thing I'm going to do in my graph is put in my asymptote at y equals -2. If you draw your graph and it looks like your asymptote's at 0, you end up missing a point. Looks like I need to go all the way up to 10. And I start plotting points. -1, 1. -2, 4. -3, 10. And again, do not get close to the x-axis, get close to your asymptote. Domain here, all real numbers. Range, we want the numbers bigger than -2. That's it for this one. All right, now I'll go ahead and practice 3 more of these graphs, including shifts for each one. I'll be looking for the following things. Did you make your table? Did you draw the graph? Does that graph include the asymptote? So be careful, pay attention to details. Other than that, that's it for this video.